integrals, and we're looking in section 6.1, areas and distances. Now, what we are trying to do is find the area under the curve, both on a given interval and just find the general function for it. Now, remember that the first fundamental question that we asked about calculus was, what is the slope of the tangent line of the curve at a given value? Like if this is, a, and this value here was f of a, what is the slope of this line right there at that point? And it turned out the answer was this, right? Turns out that was the answer. We're now going to ask the question, what is the area under the curve? And we're going to start off by asking the area under the curve. Let's say I'll have this will be our curve, for example, and we'll talk about it on the interval from A to B or something, right? So here, right, we've got all this area right there, right? And in both cases, I should have added, right, this is y equals f of x. This is the graph y equals f of x, right? And to do this, we study integrals. All right, so we can answer the question, what's the net area between a curve and the x-axis on the interval from A to B? And I say net area because we do consider area under the curve to be negative area, which is a little weird. The same way that with velocity, we considered going backwards to be negative speed, right? Negative velocity, right? And so to answer this question, we will define the definite integral of f on the closed interval from A to B, kind of ran off that, as the limit, right, for this, limit as n approaches infinity, that should seem familiar, of the sum from I equals 1 to n of f of a plus I delta x times delta x. Now you're probably wondering, what the heck is that? Well, it's this. I'm actually just gonna be a little lazy, do a little copy, duplication. I won't have to write all that again. But instead of delta x, it's really b minus a over n, right? Remember, a and b is, right, our interval, and we're multiplying this again by b minus a over n. All right, so it's that. Now, if I confused you, or maybe even scared or intimidated you, then, well, good. That was the goal. But just remember, you might have felt the same way when I introduced the limit definition of the derivative. And then we went ahead and learned it, and now we understand derivatives. So we're going to do a little bit of this with integrals. We will understand this definition, okay? That is the precise definition. We're going to start off with approximation. So we'll get to that in a few days. All right? So what do I mean by any of this stuff? Well, the way that we approximate the area under a curve, I'll just sort of do a little bit of that. Again, this is a very crude drawing. But if we're talking about this from A to B, one way that we can do it is, the idea is that curves are hard, rectangles are easy, right? So the idea is that I don't know how to find the area under the curve, but I do know how to find the area of a rectangle. Maybe I could even just do it like this, right? And so is this a perfect calculation of the area? Well, no, but it's a pretty good approximation. So the idea is that, well, maybe we could just approximate the area under the curve with rectangles. Maybe I could make that one a little bit better, just kind of do that, whatever. And let's just assume, my drawing notwithstanding, that these are all rectangles with equal width. And so if they all have equal width, then we denote the width of a rectangle by delta x, which is b minus a over n, where, again, we're on A to B, and n is the number of rectangles. Okay? Now, first what we're going to use is we are going to use left-end point rectangles. which is to say the height of each rectangle is determined by where the left side of the rectangle touches the curve. So let's just give a basic example here. Approximate the net area under the curve, blah, 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 blah. So we're going to use two left point end rectangles. And I can't emphasize enough that we are approximating the area under the curve. This will not be exact. So I'm going to draw a graph. I'll draw right here. Okay, and this, we can actually get pretty good with this one, right? So this will be the x-axis, y-axis, and we know this curve. This is y equals x squared. Maybe I should actually move this over nya. Okay, and we are using two left endpoint rectangles. Okay, and that means that the rectangle will be determined by where the left side of the rectangle begin and touches the function. So the rectangle width delta x, actually let me get this, actually no, I'll use black since the rectangle's being black. Delta x equals b minus a over n, which in this case is 2 minus 0 over n. Well, n equaled 2, so it's 1. So the rectangle width is 1. So we're going to have two rectangles. Now, if we're talking about the interval from 0 to 2, we have rectangles of width 1. You see the way of that. Okay? Pretend those are evenly spaced. Now, if we're using left endpoint rectangles, this is kind of an awkward first example, but where does the left side of the first rectangle touch the curve? Well, we know that f of 0 equals 0, right? So not the most interesting rectangle. In fact, technically not even really a rectangle. First rectangle is not actually going to be, it's just a line. It has no height, right? 0 height. Okay? But what about this second rectangle? Well, that's a little bit, that actually is a real rectangle. That actually does have some height. Right? There you go. Right? And what is the height? Well, we know that f of 1 equals 1 squared, which is 1. Okay? So that rectangle has a height of 1. And actually a width of 1. So its area is going to be 1. So anyway, the area under this curve approximately equals, so we're going to say, well, what is the length times width? Well, the length is going to be f of 0 times delta x, and I'll fill in this stuff later, plus f of 1 times delta x. So what's that going to shake out to be? Well, that's going to be 0 times 1, right? We said that. Okay? Plus 1 times 1. Right? And to be clear, this 1 is coming from here. This 0 is coming from there. Okay? All right, and so the answer we get, this approximation, is, well, 0 plus 1, which is 1. So 1 is the very crude approximation of the area under the curve. Now, I hope you see, number 1, this is an underestimate. Right, like, if you were to fill these in. Right, and number 2, this is not really close to being precise. Right? So let's try using 4 rectangles. That might give us a more precise answer. Okay, so let's try this again. Same approach. Draw some nice axes. And again, same curve as before. Same interval as before. We're using 4 rectangles though, right? So if we think about it, well, what's the width going to be? It's going to be, it's still 2 minus 0 is still a minus, or still b minus a, but now it's over 4. Actually, just remind you, delta x is b minus a over n, and that's going to be 2 minus 0 over 4, which is 1/2. Okay, so our rectangles are not, they don't have width 1, they actually have width 1/2. Let me see that. Right, and this is still y equals x squared. right? Yeah, okay. Just making sure I had that. Okay. So let's approximate the area under this curve. Well, I'm going to draw it, but you don't need to draw it, but I'm going to draw it just to illustrate what's going on. First, we have this rectangle. Then we have that rectangle. Then we have that rectangle. 3, and then the fourth rectangle. Yeah. There we go. Okay. So is this a perfect approximation? Well, still no. Still an underestimate, and still kind of a notable underestimate. In particular, look at all that area that's not being covered by that last rectangle. It's just not high enough, right? Left endpoints is what happens, okay? That said, I think we can agree it was a better approximation than before. So what is this area going to be? Well, it's going to be approximated by, well, since we are talking about left endpoint rectangles, it's going to be f of 0, right? The height of that first rectangle, times delta x plus f of 1/2. Right, that's this guy right here. Right, so the f of 0 and then f of 1/2. Right, that's that height times delta x. Right, we're just doing length times width. Right, just length times width plus f of 1 times delta x plus f of 3/2 delta x. All right, and you see that we're just doing that, right? Okay. Now, what is this going to equal? Well, the approximation is going to be, well, it's still 0 times, now what's delta x? It's going to be, we said it was 1/2, right? That was this guy. Right here, okay. 1/2. Plus, now, 1/2, what's that going to be? Oh, shoot. What's 1/2 going to be? 1/2 is going to be 1/2 quantity squared times 1/2 plus 1 squared times 1/2 plus 3/2 squared times 1/2. And we do this all out, and we get, well, let's see, we're going to get 0 plus 1/8 plus 1/2 plus 9/8, and that's 10/8 plus 4/8, 14/8, which is 7/4. Okay, still an underestimate. Okay, but definitely closer. Before we had 1, now we have 7/4. Okay. Now, of course, we could also do right endpoint rectangles. And it's the same exact thing, except we're now doing things from the right-hand side. So let's see. I'm actually going to go ahead to save time and effort and perhaps make you see how similar these ideas are. We're going to just copy this, and then we're going to just cut it. We'll just stick it over here. Yeah, I'm just gonna stick it over here, right? Now, what is changing? Well, what's changing? I don't even know how effective this will be. Well, yeah, no, this will work because I'm gonna use a different color, and I'm gonna compare it to the left, right? So instead of determining the rectangle's height based on where it touches the function on the left, we're going to do it based on where it touches the function on the right. Okay? So let's see how we do this. Yeah, so actually, let me just ignore this, and this, and this, and this, okay? So using right endpoints, do you see that this first rectangle is going to have a height of 1? Because again, we're concerned with where the rectangle touches the curve on the right. Okay? And so here we are looking at f of 1, which equals 1 squared, which equals 1. But what about this second rectangle? Well, again, we're using right endpoints, so we just kind of go up and up and up and up, and then, well, pretend it, sort of does that, right? Okay. And so this is the height of our second rectangle, right? It's at f of 2. Or it is f of 2, I should say, right? Okay. Maybe I should have labeled this somewhere else. This is y equals x squared. And look at the height of this second rectangle. Take all that up. Okay. So what's the approximation of the area under this curve? Well, it's going to be f of 1 times delta x plus f of 2 times delta x, which is going to be 1 times 1 plus 4 times 1. And that equals 5. Note that the width of the rectangles is the same. Also note that the height of this first rectangle was the height of this second rectangle. Just pointing that out. Okay. Now this is obviously an overestimate, but it's sort of the other side of the same coin, right? We still had a rectangle width of 1 because we used the same number of rectangles. We just made them a bit higher than before. Okay? So if we continue this, right, with 4 right endpoint rectangles, again, I think this is probably a little bit neater looking. I'll just copy this guy. And then we will cut it so we can stick it over here. Okay? So if we do right endpoints, again, note that this is actually the height of our first rectangle. So 0 is really no longer relevant. But 1/2 still is relevant. 1, right, that's going to be the, right, f of 1 is going to be the height of our second rectangle. F of 1/2, height of our third rectangle. And f of 2, height of our fourth rectangle. Okay, and just to be clear, this was the curve that who's let's try this. That's a little better. Right, that's the curve whose area we're approximating. Okay, so in this case, the area under the curve is going to equal, it's just height times length, or height times width, right? That's all it is. So it's going to be f of 1/2 times delta x plus f of 1 times delta x plus f of 3/2 times delta x plus f of 2 times delta x. And what's this going to boil down to? Well, remember that delta x is still going to be 1/2, right? The interval is still 0 to 2. There are 4 rectangles, so the width is still 1/2. That's going to be the same. The heights are what's changing. And again, you'll notice they're sort of shifted over a little bit, right? F of 1/2, right? I think we said that that was equal to 1/2 quantity squared. And then delta x was also 1/2. 1 squared. Right, and then in this case, we have 2 squared. Right, note that we don't have the 0 squared from before. We don't have this guy. But we do have this guy that we didn't have before. Okay, so anyway, when we do this out, again, clearly an overestimate, but not as bad an overestimate as what we had before, right? So anyway, let's see what we have here. We're going to have 1/4, so it's still going to be 1/8 plus 1/2 plus 9/8 plus 2, right? 4 times 1/2 is 2. So we're going to get 10/8 plus 5/2, which is 20/8. 10/8 plus 20/8, 30/8, 15/4, I think. Again, an overestimate. So we had 7/4 is an underestimate, 15/4 is an overestimate, but we do have an approximation. Okay. Now, I could ask a pretty loaded question, right? What is the value? What value appears to be approached from both sides? And I'm saying that it's clearly approaching 8/3. Now, if you're going, what the heck are you talking about? How did you get that, and how did you get that so quickly? Well, maybe there's a trick. Maybe there's a trick I totally didn't tell you. But what did I do in my head? And maybe I found a trick for it. Well, the way that we really get the right answer is we use infinitely many rectangles. Infinitely many. We're not going to do that now. And even then, how did I use infinitely many rectangles so quickly? Well, again, maybe there's a trick. For right now, what we're going to do is we're just going to work on approximating the area under the curve. And I'm going to use not so nice numbers, not so nice functions, not so nice numbers, okay? Approximate the area under this curve from 1 to 11 using 5 rectangles, okay? So what we can do using left endpoints, and without drawing a graph, I'm not going to draw this graph, but what I will say is that the area approximately equals, well, I'm not so sure yet. Let's find delta x first, right? We know n equals 5, and we're talking about approximating the area under the curve from 1 to 11. So delta x equals b minus a over n, which is going to equal 11 minus 1 over 5, which is actually 2. So actually kind of nice in this case, right? So the area under this curve is approximately equal to, so I guess what's it going to be? Well, if we're using left endpoints, it's going to be f of 1 times delta x plus, and then what we're going to do is we're going to jump 2, right? We're going to say f of 1 plus 2 times delta x, and then we're going to move another width over and say f of 1 plus 2 times 2. Maybe that might be a little confusing. Let me put it this way. That might be a little clearer. I'm going from 1 to 3 to 5, right? Because we're just moving over by 2 each time. And we just keep doing this until we have 1, 2, 3, 4, 5 rectangles. Right? Now, I'm not going to simplify this. That's going to take too much time. But what I will do is I will write out what f of 1 equals. It's negative 1 squared over 2 plus 3 times 1 plus 5 times delta x, which we said was 2. All right? All these delta x's are going to be 2. Plus f of 3, well, that's going to be negative 3 squared over 2 plus 3 times 3 plus 5 times 2. F of 5, same thing. It's going to be negative 5 squared over 2 plus 3 times 5 plus 5 times 2 plus, and then we've got f of 7, negative 7 squared, that plus 3 times 7 plus 5 times 2, and then one more, negative 9 squared over 2 plus 3 times 9 plus 5. That is plus 5 times 2. And again, just pointing out, these 2's are all the same. They're all delta x's. And the f of 1 is this, right? I just plugged 1 into this guy. F of 3 is that guy. F of 5, that guy. 7, that guy. 9, that guy. Okay? And whatever that equals, right? We can put that into a calculator and get an answer, right? Now, what is the approximation using right-hand endpoints? Well, if you think about it, this is all going to be the same. So, in fact, I'm just going to go ahead and duplicate this just to emphasize the fact that it's the same. And in fact, our area function is also going to be not the same, definitely not the same, but similar. right? What do I mean by similar? Well, what I mean is I'm gonna duplicate this, and you'll see what I'm saying. Think about it. Pause the video for just 1 minute and think about what will be the right-hand endpoints. And the answer is, well, we're gonna get rid of f of 1 delta x because we're using the right hand of the curve, right? Or sorry, we're using the right hand of the rectangle. So the right part of the rectangle hits the curve. So it's not going to be f of 1. It's going to start at f of 3. And then we're going to end not at f of 9, but at f of 11. Oh, I did that backwards. My bad. That guy. Okay. And so, actually, a lot of this is going to be the same, right? This is going to be the same. This, oh my gosh, I can't seem to select. This going to be the same. Well, actually, maybe I will paste that. Let's try pasting that. Oh, no. Get rid of that. Let's try copying this one more time. Plus this. Plus, and then we have one more. Negative 11 squared over 2 plus 3 times 11 plus 5 plus 2. Oh, no, sorry. I lied. Times 2. All right. So this is the f of 11. And this is delta x. Are our answers similar? Not really. Do we think either is close to the correct answer? Not really. So we've got a ways to go in order to figure out how to truly get the area under the curve. But for right now, this is a good approximation. And remember, the more rectangles, the better the approximation. But I apologize for this nonsense. That should not say that. That's the homework. Okay? And that's all we've got.